Hello, students. Hello, students. Hello. Hello, am I audible?
Yes, sir.
Yes, sir.
Okay. So, yeah, I already started a recording. So let me share the screen. So any questions on this one, the multi-threading? In the last class, just we introduced the concept of threading. Any questions on it? Yeah, can you see this slide? The benefits of threading, multi-threading applications. Hello?
Yes, sir.
Yeah. So if you just recollect, in the last week on Thursday, we just introduced the concept of threading, and then this is the holistic view of an application with a single thread and an application with a multiple threads. So this gives you an overview of the concept of threading and all, the multi-threaded process and all versus the single thread process. So you can able to see that here the process here in the towards right consists of 3 threads, and whereas the process in the left one consists of only 1 thread. And here, if you look at here, the process consisting of 3 threads. So for all these 3 threads, threads within a process, they all for all of these things were common, like the code, the data segment, and then the file systems. So all these are common across all these 3 threads and all, right? So the only thing that are differing will be with respect to the threads, the like unique to the threads will be the environment, like because each thread will have a scope of separate execution, right? So therefore, to execute these 3 threads in parallel, so we should have like for each thread we should provide the separate environment, execution environment. So in view of that, you have this stack of registers, like the stack of memory, which used to like the maintain the function calls, local variables, and so on. And whereas these register set, where any operations that are performed by the ALU and the memory transfers between the data transfer between the memory and the CPU, so that will be taken care by the set of registers and all. So in case of multi-threaded process, so only the environment, execution environment will be separate for each of the thread. Other than that, the rest of the resources, whatever the process had, so it will be shared. It will be shared. So that is a basic distinction between a single threaded process and a multi-threaded process. And then having the multi-threading, like these are the benefits, or you can say that these are the advantages. So these things we discussed in the last class very clearly, right? And then we move on to the next part, like multi-core programming. So here, the concept of multi-core programming is very much relevant and very much required when you are executing a multi-threaded processes. Because in case of multi-threaded process, the idea of multi-threaded processes will be like given a chance where a process can simultaneously execute on multiple cores, So that was the basic idea of a multi-threaded process and all. So in that context, so if the process is a multi-threaded process where you can exploit the availability of multiple cores, right, on a system, and all. So therefore, in that context, this multi-core programming is very much relevant because a single same process you can run in a multiple cores simultaneously and all. So for that purpose, what you need to do, you have to make the process to be multi-threaded, where the several instances or multiple instances of a process can run parallelly simultaneously on the multiple cores. That was the basic idea. So as the like this one, the multi-core, the concept of multi-core or multi-processor systems and all. So because of this multi-core programming for running the multiple threads simultaneously, so they have like it imposes like where the application programmers have a difficulty like to create a program to be multi-threaded process, where the application programmer when they code the program or when they write the program, so they had to make sure that they had to introduce the threads at appropriate places, and they had to see that how the thread sequence can be imagined. And if there are any dependencies, they had to take care properly. So that was the the overhead or that is imposed on the application programmers. And at the same time, you have a system designer, that means operating system designers. They also have the overhead on the multi-core programming. Suppose if you introduce the multi-threading, then we need to see that actually how these multiple threads has to be scheduled, and how these multiple threads of a process and across the process, how they have to be managed, scheduled, and how they can be controlled. So all these things are the responsibilities of the operating system designers. So the basic challenges of multi-core programming are like utilizing the multiple cores in the context of multiple threads. Multi-threaded process will be. So these are the ones like the dividing activities in a program, and the balancing, and then the data splitting, data dependency, and the testing and debugging. So here these things, no, like dividing the activities, we suppose have very complex program, and suppose you want to make it as a multi-threaded one. So you need to split that, or you need to like divide the program, divide the overall application into different activities, where you can able to introduce the threads. Each of the thread will take care of one of the activities and all. And while dividing the activities, you need to see that the activities should be balanced. That means, for example, you have a program and you divide that into 4 activities. And out of that, suppose the 2 activities will do a very minor task or minor job, and they can complete within 10 milliseconds, assume that. Whereas other 2 activities, they will go till like, for example, 60, 70 milliseconds. So in that context, if you schedule these 4 threads on the on a 4-core system, for example, 2 threads will complete much faster, and the remaining through 2 threads, they will execute to much longer time and all. So that way, in this context, efficiency of using the multiple cores is not that good. So therefore, when you are designing or when you are creating a program, so you need to see that when you're dividing the program or when you're dividing the application, all the activities or whatever the threads you are creating, so all the threads should be more or less they can provide a balanced performance, right? So that is about the balance. And then the data splitting. Suppose your program contains huge amount of data, some operations to be performed on the data, for example. So in that case, you can exploit the concept of data splitting, with which you can able to run the same operation across the multiple cores by dividing the data. For example, you need to perform some operation on a very huge data, like data consists of like we have some 1 million records, or like for example related to our census kind of a thing, right, where you have huge number of population of data will be there, and then on that population you need to perform certain task, for example. So in that case, if you can use this multi-core programming very effectively, where the data can be splitted as per the number of cores and whatever the operation you need to carry out, the same operation can be carried out on the subsets of a data, and later you can able to combine after once the data on the subsets are completed. So this is kind of data splitting. And then the data dependency, like when you are using this multi-threaded programming, and different threads will execute the jobs independently. At some point of a time, maybe the threads may need to interact. Like one of the thread needs the for making some decision, it needs some input from some other thread and all. So like what I mean to say is that there is some kind of a dependency will be there in the execution of threads and all. So that also has to be taken care. If there is some dependency, then that has to be properly synchronized. That means the threads execution has to be properly synchronized so that the desired the signal or whatever it is has to be fetched from a particular thread, and till that this thread has to be wait. So the such synchronization things has to be taken care. That is not to be data dependency. And the final one is that suppose we are dealing with a multi-threaded process in the context of multiple cores and all, then the testing and debugging is very hard, very complex thing. Because first of all, writing a code or the application programmer itself, the burden is more. Because if you want to run, if you want to make sure that the program has to run on a multiple cores with the multiple threads, then he has to do all the things like whatever I have mentioned here, like dividing the activities, make sure that those activities to be balanced and the data dependency is splitting and so on. So the writing program is one thing, and afterwards testing that program or debugging the program of this multi-threaded complex program and all, it's much harder compared to the other one, writing a program. Writing is simpler to some, with respect to, it is relative, I'm saying that, compared to the testing and debugging and all. Right, so these are the various issues when you are when you want to when we are when you want to exploit the multi-threaded processing over the multiple cores and all. And here in this context of this multi-threading or these threads and the multi-cores and all, where there are these two terms we will come across like multiple times and all. So one is the parallelism and other one is the concurrency. Here the basic distinction between these two will be like a parallelism means actually by using this multiple cores, if you can able to run a process, or if you say the multiple threads of the same process, if you can able to run simultaneously parallelly by using the multiple cores, so that kind of a thing known to be like a parallelism. And it means that you can able to use the multiple cores like simultaneously to perform the execution of the threads of a same process, or you can have the multiple processes also. That is not to be parallelism. It means that the execution, performing the execution simultaneously on the multiple cores or the multiple CPUs. It's not to be parallelism. Whereas the concurrency means actually here, it is with respect to the multi-programming. It means that suppose we have multiple user programs will be there in a main memory, and you can able to see that over a period of a time when you observe that, so all these programs you can able to see some progress. Like suppose we have 10 programs are there in the multiple main memory, and then by using a concurrency, using with the help of scheduler and all, where all these 10 programs they progressed at a different levels and all, right? Some programs may be completing, some programs may be in the middle, and some of them are at the beginning. So there are at different stages. You can able to see that all programs are in some progress. So that is that will be achieved by using concurrency. It is nothing but, even though the concurrency you can able to like observe the concurrency even with a single processor also. Even with a single processor also, it means that having a single processor, you can able to run the multiple programs not simultaneously, but in a multiplexed way, either time multiplexed or by using whatever the way you can able to do it. So with that, the multiple programs you can able to run on a single processor, and you can able to observe the progress across all the processors and all. And suppose the time that is allocated to each of the program is like, hello? Yeah, hello? Yeah. Okay. Yeah. So what I'm saying is that the concurrency is related to like a concept of like multitasking or like a multi-programming on a single processor, where you have a single processor, but you schedule the processor such a way that multiple programs can be run, and the time slots that are allocated to each process is very small, so that as a user you cannot see, or you feel that all the processes are running parallelly. But in reality, they are happening like only one process is running at a time, or at a particular instance of time. And since the time slots that are given to each of the program is much smaller, so therefore we cannot perceive that, and we feel that like all the programs are running parallelly and all. So that is the difference between the parallelism and the concurrency and all. Like concurrency means actually here you can able to see that the multiple tasks are progressing, maybe with the help of either multiple cores or like even a single core also, even a single processor also. But parallelism means actually you can see that like that means the activities can able to happen simultaneously on the multiple cores. So that is known to be parallelism and all. So like these two terms appears to be like kind of bit similar, but the way they are differing will be like this one. Concurrency means like you can able to imagine, you can able to analyze, view that as a single processor where you schedule the multiple programs on that in a scheduled way, in a proper scheduled manner, and where you can able to see that multiple programs, they have a progress. You can able to see progress in multiple programs. Whereas the parallelism is suppose you have a multiple processes are there, and you can able to run the same process across all the cores, or multiple processes can be run. It means that you can, that is multiple executions can happen simultaneously. So that is what mean by the parallelism, right? Yeah. Yeah, again, in the same in the context of multi-core programming, and these two things like data parallelism and task parallelism. So we already gone through this. Data parallelism means, as I already mentioned, that suppose we have to perform some operation on a very huge amount of data. So in that case, you can split the data into different subsets, and then these the operation, whatever the operation need to be performed, the same operation can be performed on these subsets over the multiple cores. So that way you can able to exploit the data parallelism. And anyway, the task parallelism is nothing but a concept of multiple threading and all, multi-threaded process and all. So that means you can able to run the multiple tasks parallelly, simultaneously, where each task will perform a unique operation and all. So that way, these two kinds of like concepts will be exploited in the multi-core programming and all. And then, in addition to whatever the threads, multiple threads or multi-threaded process, whatever we are discussing, so those threads are like they are introduced in a software or nothing but in a program. That means either the user will introduce that or a compiler can introduce that somehow where the program can able to run parallelly, where by using a multiple threads and all. So though the concept of threads or the threads are known to be like they are created by software, that they are, you can say that there are software threads. They are like software threads, right? That means the threads are created by user or nothing but by a programmer and all. So or like the other one, like a compiler can also create threads and all by knowing the structure of program, whether it's a loops or whatever and all. So there it can automatically introduce the threads also. That we'll see that later. So those are the software threads. To support this multi-threading and all, even the hardware also will support by creating the threads. Like one way is that actually hardware will support those multi-threading. One way is that by providing the multiple cores, and not only that, for every core, it provides the multiple threads, multiple hardware threads. That means, for example, you have like a dual core system. That means there are two processors there in the same chip, and each process will in turn can support the multiple threads, right? So those are not to be hardware threads. That means on each processor, you can able to place the two threads. You can use the two threads, and these two threads are used in a way that actually, for example, suppose when you say that a processor having a multiple hardware threads, what it means here is that a processor is running a particular instruction, or that instruction is basically to fetch the data from in the memory from a memory. So first it will check the cache, right? Suppose because the cache accessing is very fast, so therefore within a cycle or within a few cycles you can able to fetch the data. So therefore the thread execution will continue. Suppose for example, when you fetch the data from a cache, if the data is not available in the cache, that means cache mesh occurs. At that time, you have to go to the lower level cache, or otherwise you have to go to the main memory. So, but that will be time consuming. That may take some 10 cycles or 50 cycles, depending upon where the data is there. So at that time, instead of waiting for the data, you can use the other thread. you can use the other thread for running the for making use of that particular CPU and all. So that way here, even the CPUs can have the multiple threads where they can able to switch the threads based on the instructions and all. Suppose if it is a memory bound instruction and where the data fetch the memory and getting the data from a memory, it takes more time. So in that context, you can use the other threads with which the programs can be run, where the other threads may require the need to perform some computation where it has to perform the computation from the register contents using the ALU and so on. At that time, you can, so that way you can have a hardware threads that supports these like whatever this I'm saying the these multi-threaded architectures and all, right? And sometimes there are examples. Sometimes there are some process which supports the 2 hardware threads per process, and there are some process which supports 8 hardware threads. There are 8 cores, and where each core supports the 8 hardware threads. And that depending upon the application and whatever you are using, and if the application requires the memory access and all, more memory access and all, at that time one can use this hardware, explore this hardware thread so that the CPU can be effectively utilized and all. And this is just an whatever we discussed, the difference between the concepts of concurrency and the parallelism. And suppose a concurrency means basically we'll try to visualize that on a single processor, and where if you want to run the multi-threaded process on that, a single processor time will be scheduled across the threads. For example, there are 4 threads, a process contains 4 threads, and these threads are scheduled with respect to time, right? This way, like thread 1, 2, 3, 4, and so on like that. And suppose if you have a multi-core system, consists of 2 cores, for example, where you can run the 2 threads simultaneously, T1 and T2. You can see that in the same time slot, you can run the T1 and T2, right? And then after it's over, then T2, T3 can be run. So this is way like this is in the here the context here in this context, it's a dual core processor where her 2 cores are available, where 2 threads can simultaneously execute, can be executed. If it is a quad core, then all these 4 threads can simultaneously be executed. So that way, the concept of concurrency and the parallelism will be different between a single processor and a multi-core processor. Yeah, the next one is that like in the context of multi-core system, where the idea of multi-core system will be like you can speed up the execution, provided if the application can able to run through multiple threads. But in the application, if you want to introduce the threads and all, the application should be parallelizable. That means whatever the program, if it is parallelizable, then you can able to introduce the threads appropriately and you can able to run these parallel portions, right? So therefore here, the speed up in execution that depends on like the components, the various components of a program. That means in a program, a certain portion can be can run only serially, whereas the remaining portion you can able to run parallelly at any iteration, at any way, at any interleaving you can able to do that. So in that context, where even though you have a multi-core system, and the performance of a multi-core system or the speed up that can be achieved by using a multi-core system, that depends on the serial component. Because the serial component means even though the other things can be executed on the parallelly on the other threads, but this cannot be splitted. This particular serial portion, whatever is there, it cannot be splitted, right? So therefore, the speed up that can be achieved using a multi-core system will be limited, or can put some limit on based on this serial portion, the content, how much portion of the data program has to be executed serially and all. So that way, this particular formulation will provide you the how much speed up that can be achieved by using a multi-core system. So here you can see N is nothing but number of cores, where S is going to be like the portion of the code that can be executed only serially. And 1 minus CS means this is the component of, this is the remaining portion of a program where you can make it parallel. You can parallelize that one. And then the number of partitions you can parallelize, that depends upon the number of cores. as the number of. So even though the number of cores is very large, right? So this component can be nullified, but the other component, whatever, yes. So this has to be executed in a sequentially. So therefore, the speed up will be limited by this one. What is the amount of in the program? How much? What is the proportion of the or what is the portion of the program which has to be run serially? So that dictates the amount of speed up and all. Right. So you can see that you can given some numerical examples and all. Suppose the 75% of the code can be parallelizable means you can able to achieve by using a two core system, you can able to achieve the speed up of 1.6 times, right? Because the 75% means here the SC will be like a 0.25 or 25%. So with that, and since it is a two core system, and you can able to see that n equals to 2, and then if you keep yeah, the next one is here we'll try to see that how these threads are implemented in a system, right? So there are like user threads and kernel threads. We'll see that what is meant by user threads and kernel threads and all. So user threads means, so whatever the threads that are created by application program, so those threads are basically the managed, created, and the communication, whatever, or the controlling of the threads, everything will be done at a by using the user level thread libraries and all. It means that the entire activity controlling of threads or management of threads, so that will be done by a thread libraries where those thread libraries are placed in the user space, in the user space. And whereas the kernel threads means where the kernel also can support the threading. It means that suppose we have a user level threads, the application, the programmer will place the threads in the program. And for running those program, you by exploiting those threads, where the kernel has to give the support, because ultimately the kernel has to provide the resources or can allocate the CPU time or can perform the CPU scheduling. Everything will be actually carried out by the kernel and all. So if the kernel is not aware of the threads means then the threading will not be supported by the kernel. So you cannot achieve much the advantage of the threading or multi-threaded process and all. So yeah, here the user threads means here the thread management or the thread activity is managed and controlled everything by the thread libraries where those libraries are placed in the user space, right? So it means that here in this context, if there are only user threads that are used for performing a multi-threaded process, for execution of multi-threaded process means a kernel is not aware of that one. So to perform the effective like utilization of this multi-threaded process execution, the kernel also should be aware of that. That means kernel also should support the user threads, whatever is created by the application programmer and all. So that way, these kernel threads are nothing but like the kernel also support the threads that is provided by the user and all. And with that, you can able to achieve like the better concurrency or better parallelism and also that can be achieved. And with that, you can able to get even the response time is faster or even the execution time also can be optimized. Right. So these are the examples of that means the user level threads are can be supported by the system. And now the most of the operating systems support the kernel threads and all. Yeah, we'll see the details and then it will be clear to you. And the multi-threaded models will be supported by like these are the three different approaches with which you can able to implement the multi-threaded process or the threading can be concept can be implemented either at a user level or at a kernel level or at both. So we'll see one by one and then it will be clear to you. Like many to one model means here in this, the user space, a process can be represented or a process can create a multiple threads. A process can create a multiple threads in a user space, but the kernel will not support that. That means that kernel is not aware of that. So whatever the threads that are created in the user space, so all these threads are mapped to a single kernel. That means the kernel is not aware of that one. That means the kernel will provide only the single execution, will provide a single execution. And all these threads, whatever is there, all of them will be treated or will be not aware of the kernel. And it means that the kernel is not aware of the threads. Like suppose the execution is happening, then it feels that yeah, the kernel will assume that yeah, process is running. a process will be running, and it doesn't know that in the process there are threads, and now the thread 1 is executing, and afterwards thread 2 is executing. So those details, and those are not aware of the kernel at all, and they are they are known by the thread library or the thread management system, which is present at the user level and all. So here in the many to one model, the idea here is that the user, or there are several threads that can be created, right, in the user space, and all these threads are managed or controlled by the thread libraries that are present in the user space and all. And the kernel is not aware of that one. But finally, the kernel used to perform the execution of these sequences by using the CPU. So since the kernel will kernel will not know about these threads and all. So therefore, there are certain issues over here. It means that, suppose, for example, assuming that there are 4 threads of execution, there are 4 threads are present in the user in the process and all. And by using the thread library or functions, whatever is supported by user thread library, here to some extent the thread management will be done by this user thread library and all. And as long as these threads, they doesn't require the kernel help, these things can be properly managed by the thread library that is available at the user space and all. So what it means is that, for example, you have this thread, and then this thread is continuing, for example, and after some time, if you want to switch the thread, switching these threads and all, that is not known to the kernel and all. That has to be carried out by the thread management that is present in the thread supported by thread library in the user space and all. So that will be done by the thread library that is supported at the user space and all. Those are not aware of the kernel and all, because here the kernel is not aware of the threads that are present in the process and all. So here the thread management functions that are supported by the user thread library will support this one for thread switching. All these things will be done by the thread library and all. So that is one thing. And another thing is that, suppose a particular thread is running, for example, executing, right? So when it's execution, suppose at some point of a time, this particular thread may need the IO, some IO is required. So at that time, so for performing IO, that means the input or output operation, for example, then the user space or the user program or the thread libraries at a user level, they will not support that. They in turn requires the support of a kernel and all, right? Suppose an IO is required for a particular thread, for example, then they request the kernel to do that. And when they request the kernel, and the kernel will see that what is the system call for that particular IO that is required. If the particular system call is a blocking system call, then at that time the kernel will block the entire process, because suppose you require that the input is required from a keyboard. Then when you are performing that particular IO function, that is nothing but scanf function here. So that internally call the system call. So that system call has to be handled by the kernel, and that is the blocking system call. We know that. So since it is a blocking system call, then the kernel then this kernel will switch the process, because the kernel is not aware of that. This blocking system call is performed by this particular thread and all, and there are other threads are available in the process that is not known to the thread. It is not known to the kernel. The kernel will simply block the whole process and then switch the process, and some other process has been allotted to the CPU. So those are the issues in the case of this many-to-one models and all. That means that if any one of the thread is blocking, will generate a blocking system call, then the entire process will be blocked. Entire process will be blocked, and nothing but entire process will be switched from the CPU, and some other process will be placed into that. So that is against to the concept of threads, because the thread says that actually any one of the suppose, for example, what I'm saying is that if a process has 100 milliseconds of time, for example, time slot, and in that one process is executing, and at some 15th millisecond, this particular thread needs the IO, right? Immediately, then as per this particular process, right, this particular thread requires the IO, and then to execute this IO, it takes the system call, it calls the kernel, and the kernel will execute the system call. This system call is a blocking system call. Then immediately the kernel will switch this process, and some other process will be placed over here and all, right? But now here there is a time slot of 100 milliseconds, but only the 15th millisecond this has been occurred, And even though there is a chance for another 85 milliseconds, the process can run, but still it's not happening. But still you cannot, but still kernel will not allow that, because the kernel doesn't know about these threads that are present at a user level. So with that, the blocking system calls create a problem in case of many to one model and all. And not only that, in this case of many to one model, where this threading is not seen by the kernel, so the kernel, even though there is a multiple, suppose the system has a multi-core system, but the kernel will not able to provide, will not able to provide the execution of these multiple threads parallelly. Because here the kernel is not aware of the threads, even though the system has a quad core system, there are 4 cores are present, but the kernel will not schedule these threads on these 4 cores parallelly, because the kernel is not aware of the threads and all, and it will treat this whole thing as a process. So for a process, it will give only 1 core for CPU execution, right? And it is up to the user libraries, they can switch these threads within that time. Suppose 100 milliseconds the time slot, and then these user thread library can switch these 4 threads parallelly, not parallelly, 4 threads like the one after another. That means maybe 25 milliseconds to this thread and another 25 milliseconds. Likewise, the thread switching can be done by user program, by the user thread library, but it's not aware of the kernel and all. So what I mean to say is that even though we have a multi-core system, we cannot exploit the capability of multi-core system for this for execution of this multi-threaded process and all. So these are the issues in case of the many to one model, and so therefore this is not at present it's not being used, right? But this is one of the model where the idea here is that here whatever the threading and management, everything is done in user space. The kernel is not loaded at all. The kernel is not loaded, and the entire activity will be done in user space. So therefore, that can be done, carried out much efficiently without intervention of the kernel. You can able to do that. But the problem is that if these threads requires the help of a kernel or need to execute any system calls and all, at that time they need to interact with the kernel. And if that system call is to be blocked, at that time the entire process will be blocked. So that is the major problem. And another thing is that the parallelization cannot be done, cannot happen here and all, because the kernel is not aware of these threads and all, even though we have a multi-core system, but these threads are not scheduled, are not executed parallelly by a multiple cores and all. So those are the major drawbacks of this system. And the other approach in the context of multi-threaded system, multi-threaded process will be one-to-one model. So here, in case of one-to-one model, the idea here is that whatever the threads that are created in the user space, each thread will be mapped to kernel thread, is mapped to a specific kernel thread and all. So it means that, for example, in the user process, when it's running, it creates 4 threads. It means that whenever a thread is created in the user space, and that particular thread is mapped to an associated thread at the kernel level. So it means that whenever the user thread is created at the user level, a corresponding thread is also created at the kernel space also. And these through the thread at the user space, it is mapped to this particular thread in the kernel and all. So that way, since the kernel is aware of that, actually here, yeah, there is a process, and this process is created in threads. And whenever the process creates the threads, and it also invokes the kernel threads also. So that way, if a process creates 4 threads means, then the kernel also supports these 4 threads using 4 threads at a kernel level. So with that, actually, whatever the drawbacks we have mentioned earlier, so those things will be taken care of that. It means that a particular thread is executing, for example, and if that thread requires IO, and then it calls the kernel thread, and this kernel thread will see that will take care about the IO by executing the system call. And if that system call is blocked, then the other thread will be placed. Then the switch will be done within the threads, because the kernel is aware of that. There are another 3 threads are there, and this particular thread is in the blocking. So therefore, you can place the second thread will be scheduled over there. So it means that here basically the kernel will take care of the responsibility of a thread management, thread scheduling. All these things will be taken care by the kernel and all, right? And not only that, here the kernel also will take care about the parallelism also, because the kernel is aware of that there are 4 threads of this process. If there is a multi-core system and the cores are available, then multiple cores or these multiple threads or these threads of a same process can run on the multiple cores also. So, but here the problem is that overhead. So each process will generate whatever the number of threads that are required at the user space. So the equivalent number of threads are need to be supported or need to be generated at a kernel space also. And it is an overhead because each thread has a different execution environment and all. And for managing that one, like as we have seen that a process management, we have seen a process control block that is managed by the kernel. The same way here, the kernel has to manage the process in terms of as well as the process control block as well as a kernel or the thread control block also. And since we have a 4 threads means for every process, it has to maintain these 4 thread control blocks because these 4 threads are like 4 different execution sequences, right? And the status of this particular each of the execution sequence is maintained by the kernel and all. So that way, the overhead will be more as you increase the number of kernel threads and all, right? So that's what the number of threads per process sometimes will be restricted because of the overhead. Suppose as the process to be have more flexible to have more efficiently to perform its execution. If you generate so many threads and all, then to support that in the case of one-to-one model, the kernel also should generate so many threads and maintaining and managing the several threads of a process is very hectic and it generates a lot of overhead. So with that, even though whatever the advantage of multi-threading that we introduced at the user space, so that will be burdened to the kernel to support all these threads and all. So that means there should be some kind of a limit should be there with which the kernel can support only the finite number of threads for the user threads. So this is about one-to-one model. And so this one-to-one model is just quite contrast to the many-to-one model. In case of many-to-one model, the user space supports the threads, but the kernel space will not support any threading at all. So therefore, in most of the applications where you have a problem like blocking the whole process, or even though we have multiple cores and all, the parallelism cannot be achieved. So those are the issues with that. But all those things can be taken care in case of one-to-one model. But the problem with the one-to-one model will be like the kernel will be overloaded because of the several threads that has to be maintained. The other one is the many-to-many model. So here in the many-to-many model, the idea here is that here it takes the advantages of both. Like in case of many-to-one model, where the kernel is not loaded at all, right? Because the kernel is not aware of threads at all. So the kernel is not at all loaded. And the user space where we have as many threads it requires, it can able to create, and where the entire thread management will be done at the user space only. So it is advantage. But the problem is that, but the user threads, when it requires the services of operating system, that's where the problem is. That means the operating system will block it, and the operating system will not run the threads in a parallel manner. So those are the issues with the one-to-one model. In the many-to-one model. But in case of one-to-one model, we have all the advantages. But the only problem is that kernel is severely loaded, right? So therefore, in case of many-to-many model, it takes advantages of both. It supports the user level threads, like whatever the user application, whatever the number of threads it requires, it supports. It can able to create as many threads as it requires. But the kernel will support only finite number of threads. Right? The kernel will support only finite. That means the user space you may create some 20 threads for a process, but the kernel can support only 5 threads, for example, only 5 threads or 6 threads. That depending upon here the number of threads that will be supported. So that will be dictated by the underlying hardware and the memory space that whatever is available, and the other aspects and all, even the application program also. So that way the number of threads that is supported by kernel are limited or finite. So it will be always less than or equal to the at most. It may be equal to the number of user level threads and all. So this is the many-to-many model. So with that, the kernel is also not heavily loaded. The kernel is loaded, but it's not overloaded, right? So whatever the kernel can able to support, it can able to support with the finite number of threads and all, right? So this is about the many-to-many model. And then the other one, the other one is known to be two-level model. And here this two-level model, usually it supports, it's kind of many-to-many model, And in addition to that many-to-many model, it also support for certain applications where some thread, one or two threads, they are very important, very crucial and all. And they have to be given, they have to be prioritized, and they have to be given proper attention and all. So in that case here, where the kernel will support this many-to-many model, and there are for specific threads, these specific user level threads are bound to the specific kernel thread and all, specific kernel thread, right? So what it means here is that, so suppose for example in the user process, as I mentioned, we have some 20 threads were there. Out of that, there may be one or two crucial threads are there, and these two threads, they have to be allocated the kernel threads, like specifically, or like are binded to a specific kernel threads and all. And the remaining kernel threads are used to be mapped to the remaining the user space threads and all. So it's going to be two-level model and all, where it supports some user threads are bound to a specific kernel threads, and the rest of them are bound to are mapped to the remaining kernel threads and all. Remaining kernel threads. It's going to be like a two-level system and all. Yeah. Then the thread libraries, as we already know that for performing any activity like supported by the operating system and all, you need to have some APIs are required. So with which the application programmer will make use of the operating system services. Similar to here also. Suppose we want to introduce a threading concept and all. So the threads has to be supported by the operating system. So therefore, a thread library is nothing but the API which provide the support to the programmer, or which the programmer will make use of this API. So with which he can able to write the thread functions. So with which the threads can be created, or threads can be terminated, or threads can be managed, scheduled. You can able to do that. And again, these thread libraries, as we have seen that, so these thread libraries, they can be there in the user space, or they can take the help of the kernel. Like the first one, whatever we have mentioned, like many to one model, where the entire all the entire thread libraries or the thread support will be done in the user space only, in the user space only, or mostly it is carried out by user space, right? But with that, there are certain disadvantages were there, right? And for handling that, the threads are supported by the kernel also, right? So we'll see that the thread library, how, and as we have seen that in case of POSIX system, it supports the threads using a pthreads. And so here, in case of this POSIX system, here it's not that we are not bothered about how these concepts are implemented. Here they just specify that, well, what are the specifications? Suppose what are the thread functions and what are it's supposed to do? Like what is its the objective of that? Like it provides the specifications, and it mentions about the behavior of that particular function center. And the implementation is that up to the operating system, the way it can able to implement. And this is a simple example where how the pthreads can be used for creating a thread and maintaining, managing a thread and all. So here you can see here this example is you have a main program, and in this main program you have a function call where that function used to compute a sum of the numbers, where we'll specify one number. It will compute the sum up to that number, like all positive integers starting from 1. It will sum up to the number. Suppose when you say 8, the function will try to compute the sum up to 8, 1 plus 2 plus 3 plus up to 8. Right? Suppose 15 means up to 15. So that is the function call, and that function call is will be called from this main program and all. And so this is the function. The runner is the function name. And then we are passing the parameters, nothing but what is that number, positive number. Like when you say 8 means it will compute this particular function, will compute the sum up to 8, like 1 plus 2 plus 3 up to 8, something like that. Right? This is a function call. And we call this function from this main function. And so therefore, here if you want to introduce the threading means, anyway, the main function, the main program, it has one thread of execution. And then this program is calling some other function, like one more function. It's not to be like the runner and all. So if you want to introduce the thread, you can able to introduce the thread where the thread will be implement this, or where thread can execute this function and all parallelly, right? So that way you can able to introduce the thread. We'll see that. So here this is the function call and this is the sum. It's a it's a global variable, right? And then this is the main function. And here, since we are using the threads and all, so therefore the thread ID will be defined here. It's an integer number. And the thread attributes has to be initialized. So we are just declaring that attributes and all. Later we'll initialize that. And these are the initial checks about the basic program, right? And afterwards here we need to give the attributes to the thread. Attributes to thread means like kind of scheduling information and some other information like. So these are the thread attributes and all. Here we are not providing. So therefore the default attributes it will be taken. And afterwards we are creating a thread. So using a function like a pthread create is a function. And then the arguments are like a thread ID. Then attributes, whatever here we initialize, these attributes has to be passed. And then the runner, it means that, so this is the starting address or like from where the thread has to start its execution and all. So runner. And then this gives you the, what is the number? Like suppose here this particular function call, it tries to compute the sum up to the number, up to some positive number. That positive number is provided by this argument and all. So likewise, this is the thread create function with which the thread will be created. And then afterwards, what we are doing, the pthread join. Pthread join. That means that here in the main program, we are creating a here thread and all. And creating a thread, and then that thread will be executed. Then afterwards, immediately we are passing that thread join. That means, for example, here, assuming that here up to this point, we have only one sequence of execution, right? It's a main program and all these checks will happen. And here and all, and here the thread attributes we are passing. And afterwards, here we are creating a thread. The moment once you create a thread, you have two execution sequences are there. One is the main thread already there, the primary thread. And now one more thread we have created. That means now here the two threads are there. That means two execution sequences are available. And from these two execution sequences, based on the thread, one of these execution sequences will be scheduled. Either the main thread may continue or whatever the created thread that may continue, right? So here our idea here is that at this point of a time where we have the two execution sequences will be available. And then based on the scheduler, so one of these threads will be scheduled. Suppose if it is a single process, I'm saying single processor. Either the newly created thread may be scheduled or the main program or the main thread may be executed. Suppose assuming that after just creation, immediately the scheduler has given to the main program, the main thread will be to be executed. So then after the creation, here the main thread will be executed. The main thread here, it includes this particular command, pthread join. It means that it's similar to that in the parent child. After creating a child, the parent will wait. So similar to here, as per the requirement here, pthread join means it's kind of wait function. Pthread, that means it will wait for this particular thread to complete thread TID, right? And then once this this is a wait system call. This is just pthread join is nothing but it just wait for, it is a blocking system call. It just that means the main thread will be when it executing, this means it is just waiting for that. So it will be unblocked only when this newly created thread execution is completed or terminated, right? So where is the new thread here? The new thread is this one. The new thread is nothing but this is the entire program. The new thread, when after creation, it starts execution from the runner. The runner is nothing but this one. That means the new thread starts execution from this point, and then it will execute the content or the instructions here. And then when it reaches to the last statement is a pthread exit. Pthread. It means that here after coming to this point, it exits. That means that whatever the thread is running, and now the thread will be exit. That exit means it will terminate. So it means it is a last statement. It exits with a 0 status. And now when this thread exits, whatever the status that is returning, so that will invoke this wait system. Not wait system call. This is pthread join, because the main program is waiting here and all, and here this thread is completed. Right. Once this thread is completed, we have only one more thread. Only the main thread is remaining. And now the main thread, once it is terminated, the main thread will be unblocked. Earlier, the main thread is blocked on this system call for completion of this particular thread. Once this thread is completed, then this will be unblocked, And with that, it will come to know that what is the TID, which is terminated. So then it is unblocked. Then it starts its execution from here. Then this will be executed. Then the sum, whatever is there, the sum will be printed. So what is this sum? The sum is created, or the sum is computed by the thread, the newly created thread and all. So this sum is computed, and afterwards, now the main thread will print the sum. And here you can see that the sum is a global variable. So therefore, both the threads can be executed, and whatever the sum that is created over here, we are not returning at all, just created. So that is there in the sum, and that sum will be printed out. Right? So that way the threads will coordinate and perform its execution based on the requirement. Here in this case, once the thread is created, then the main thread will be wait, because the main thread's job is it has to display the sum. And for displaying the sum, sum has to be computed. So therefore, immediately after creating a thread, the main thread will simply wait for completion of the thread, newly created thread. Right? Once the newly created thread is completed, terminated, then it unblocks, and then it prints the desired sum. So the same way here, you can create the multiple threads also, and then you can wait for the multiple threads also. You can see that. And then this is the example for a Windows environment, how the threads are created and all. It's almost similar to that. Yeah. And the next one, what we are going to discuss here is that it's implicit threading. So here the concept of implicit threading means, so far whatever we discussed about threading, thing is that when the application programmer writes a program, or when he starts coding the program, and if you want to introduce a multiple threads and all, so he has to he should have an idea about what the actual program, what the actual task will be, and he will try to divide that into the different components. And for each component, he may introduce the threads, and then that way the threads will be introduced. If it is a bigger program, if it is a very complex task and all, introducing threads by an application programmer will be very difficult at all points. And he can introduce the threads at a gross level, at a very broader level, or at a conceptual level and all. But in the program where you have scenarios where you have opportunity to introduce a threads at several places, we know that, like for example, we have a for loops are there. That means for performing some operation and all, where the several iterations will happen. In each iteration, the same operation has to be carried out on different data, right? So therefore, all these things, for every place where the application programmer has to introduce the threads and monitoring the threads and all, it's very hectic. It cannot be done. So therefore, the implicit threading is nothing but creating and managing the threads done by the compilers or the runtime libraries, rather than programmers and all. Programmers, he should have an idea about, at a very broader level or a conceptual level, he should have an idea about like how this program runs and all, what are the various independent components or parallel components and all. So that way he will introduce the threading at a very broader level. But at internally, the threads are created automatically by the compilers or the runtime libraries, where it will identify that when it compiling, it just identify the instructions and all, where if there is a chance for like a repetition or like a kind of a parallelization can be possible, then the threads will be introduced. Threads are created, and then with the created threads, that parallel code will be run across the multiple cores and all. So that way, by using compilers and runtime libraries, where you can able to create and manage the threads automatically, without programmers, without really the programmers to do anything here. So this is not to be implicit threading and all, right? That means threading will be carried out automatically without the knowledge of a programmer and all. And so these are the different methods for the implicit threading, like thread pools, OpenMP, and a grand central dispatch and all. And there are other methods supported by Microsoft and other things. So we'll discuss these things like one after another. First, we'll try to introduce the thread pools. So here the thread pools means here, the idea here is that, as we have seen one example at the very beginning when you are introducing a threading, like for example, you have a web server, where you have lots of requests used to be there for a particular web server, and lots of clients, they used to request for a particular web page. So therefore, the web server, what it will do, it will create a thread for every request, and then that request will be passed on to the thread, and the thread will take care of that. So here, suppose the requests are too many. So in that case, for every request, it has to create a thread. Then afterwards, it will pass the request, and again, the process has to be like wait for the listeners and all, right? So it takes a lot of time creating a thread, then assigning the or passing the request to the thread and all. It is taking some reasonable amount of time. So to overcome that, the idea here is that for these applications where when you have lots of requests where the thread creation is required, and also at that time, instead of creating threads whenever the request arrives, instead you can create a threads at the beginning itself. That means whenever you start the runner, whenever you start the server, for example, at that time itself you create a threads, some finite number of threads you can create it. And now the threads are waiting. That means the threads are available, right? So they are waiting in the pool. And whenever the request arrives, so immediately the request will be passed on to a thread. That means we'll just invoke one of the thread, and then we'll just pass the request. Right, and then the thread will take care of the request, and then it will respond to the that request, and then again the thread will go and wait in the pool, wait for some other job to be done. So this is known to be thread pool. It means that at the beginning or a priori we will create a sufficient number of threads or some number of threads and all. Then afterwards, whenever the request arrives, then simply assign to a different threads for each of the thread and all. So here the number of threads in a pool, that depends upon this one, like the number of cores, and then the amount of physical memory, and the expected number of requests, right? So based on that, you can able to vary the pool size also dynamically, right? For example, at certain time you have so many requests and all, and at other times the requests are very less, like less than half of the time, half of the peak request. So at that time, every time maintaining the threads, the pool size to be larger is not advisable, because it takes a lot of resources and all. So therefore, you can vary the size of the pool also dynamically, right? And yeah, dynamically we can vary the pool size. So with that, you can effectively utilize the resources and all. And there is again the APIs to support this thread pools and all. So yeah, here you can see that the thread pool, the idea here is that simplicity just based on the application, we create several threads, and then these threads, these pools will be maintained, and whenever the request arrives, immediately the request will be passed on to the threads. And another advantage of this thread pool is nothing but, otherwise suppose there is no thread pool, for example, and whenever the request arrives, you are creating a thread and then you are passing that. Likewise, suppose there are several requests that each time when they are creating, and you don't have bound on number of threads that are creating, right? So therefore, if you have a thread pool, then we will specify the number, the size of the thread pool. Suppose you say that they can able to support only up to 100 threads. The pool size equals to 100. So we cannot cross beyond that. So only 100 threads are available, and if the requests are more, so then in that case, if all threads are engaged, then the request will be pending. That means the request will be kept waiting in the queue and if one of the thread is available, then again the thread you can pass the request to the threads. No, one advantage of the thread pool is that since the thread pool will fix the number of threads, so therefore the exhausting of resources and all those issues will not arise at all. Otherwise, no, if you keep on creating a thread whenever the request arrives, and during the peak times and all, there are several requests will be there, and you are keep on creating a threads and all, at that time, like the most of the resources are memory space and all these things are occupied by threads of a single process, right? A server process and all. So that creates a problem and all. So to overcome that, thread pool is one of the situation. And another thing is that efficiency also. Each time separately creating a thread, instead already the threads are available, generated, they are available there. And then passing the request to thread is much easier, much simpler. So this is the concept of thread pools and all. And later we'll discuss about the next class tomorrow. We'll discuss about the other aspects of the implicit threading. And after that, we'll discuss about the different issues. What are the issues that are there in implementation of threads and all. So those things we'll discuss later. Okay, we'll stop here. presenting.